Okay, so hopefully this stuff is going to be pretty much review for you. And there'll be a couple of new things when we talk about ionic compounds that you won't have talked about in Science 9. It's nothing like super difficult or anything. It's just a little thing they wouldn't have gone over in Science 9 with you. Okay, and then all the stuff to do with molecular compounds will be exactly the same as what you learned in Science 9. So hopefully this stuff all seems familiar. Okay, so the first thing we got to be able to do is identify a compound as ionic or molecular. Okay, so this compound here, would that be ionic or molecular? Okay, so we have magnesium chloride. What kind of an element is magnesium? Metal or non-metal?
Metal.
It's a metal. Okay, chlorine is a non-metal. Okay, here's how we tell the difference. On your periodic table, and I'm going to pass these around here in just a minute. Okay, on the periodic table, we've got metals on the left-hand side of the staircase, and we've got non-metals on the right-hand side of the staircase. An ionic compound is always made up of a metal and a non-metal. Okay, so anytime you see both, you're dealing with an ionic compound. A molecular compound is made up of two non-metals, two or more non-metals. Okay, everybody got me there? All right. Okay, so this compound then is ionic, and this compound here would be ionic or molecular? Okay, is phosphorus a metal or a non-metal? Non-metal. Is oxygen a metal or a non-metal? Non-metal. They're both non-metals, so this is molecular. Okay, that's how we tell the difference. Okay, we're looking at whether, basically, if it has a metal in it, it's ionic. Okay, the first thing in the compound is a metal, it's an ionic compound. All right. Okay, so now that you got your periodic table in front of you, you can see the staircase there is kind of a black bolded line, right, that is separating the left-hand side, which is much bigger, of the periodic table from the right-hand side. Okay, the right-hand side is the non-metals, the left-hand side is the metals, okay, and that's the separator. All right, so the second thing we've got to be able to do is write formulas and proper names for chemical compounds. Okay? And hopefully that's going to seem familiar when we start going into it. All right, so we'll start off with ionic compounds. Okay, so ionic compounds occur, like we just said, when a metal from the left-hand side of the periodic table and a non-metal from the right-hand side react to form a new molecule. So if I had an atom of sodium react with an atom of chlorine, I would get sodium chloride. Okay, an ionic compound that we use all the time is what? Salt. Yeah, it's common table salt. Right? Now, salt, the word salt, actually refers to any crystalline ionic compound. Okay? All ionic compounds are crystalline solids at room temperature and are generally referred to as salts. This is the most common salt, so we refer to it as salt. But okay, in chemistry, if I write NaCl, write the name of this, don't write salt. Okay? Salt is a general term referring to all ionic compounds. This needs to be named specifically sodium chloride. Okay? The only compound you can write the common name for is water. Okay? Everything else needs to be named according to proper naming rules, which is what we're going over today. Okay. So in these molecules, electrons are typically lost by the metal and gained by the non-metal. Okay? So reactions happen and compounds are formed according to kind of what Dalton said. Okay? Dalton said that atoms can combine in simple whole number ratios to form compounds. Okay? The question is, well, why would they do that? Why do compounds form in the first place? Okay? Well, the reason being is they represent a more stable form of something. Okay? So if I have sodium, okay, a sodium atom has an atomic number of 11. That means it's got 11 protons and 11 electrons. Something Bohr discovered is that electrons, or so let's say atoms, like to have a certain arrangement of electrons. They become more stable when they have a certain arrangement of electrons. Okay? He thought it still was like the planets around the sun, which we said is somewhat true. If you took a picture of an atom, it might look like that. Okay? But what he found out was in the first energy level surrounding an atom, there can only be 2 electrons because it's small, and electrons are all negative and they repel each other. So, and you'd only be able to get 2 sitting in this first energy level. Okay, the next energy level above that can hold 8. Okay, their repulsion actually causes them to form what are called lone pairs. Okay, that actually forces 2 of them together so that there's space between the pairs. Okay, now that's 10 electrons. There's still 1 more. Okay, so this next energy level, the last one, can hold another 8 electrons, but it only has 1 in it. Okay, what Bohr discovered is that atoms like to have their outer shell of electrons, their outer energy level, whatever it is, full. Okay? Atoms are more stable and more happy, if we're personifying them a little bit, when they have their outer shell full. So if we're looking at sodium, sodium's outer shell can hold 8 and has 1 electron in it. What would be easier for sodium to do? Find a home for that electron, or find 7 more? What would be easier? Because it can't just throw it away. It has to put it somewhere. Okay? So it's either got to bargain around and find 7 more electrons to fill that outer shell, or find 1 person who wants 1. What's easier? Well, get rid of 1. Yeah, get rid of 1 is way easier. Find a home for that one. Okay? Chlorine is the perfect match for sodium because chlorine has an atomic number of 17. Okay? If we draw chlorine, okay, its first shell has 2 electrons, it's full. Its next shell has 8 electrons. It's full, that's 10, okay? Its next shell has 7 electrons and is capable of holding 8. What's easier for it? To find homes for 7 or pick 1 up? Pick 1 up, okay? And this is what happens in ionic bonds, okay? In an ionic compound, there's a weak bond formed between the metal and the non-metal, okay? Because they are trading electrons, okay? So sodium will give its electron to chlorine. Now they both have a full outer shell, but now they're both charged. Okay? When sodium had 11 electrons and 11 protons, its charge was 0. Now it's lost an electron. Now its charge is positive. Positive 1, in fact. Okay? Because now it has 10 electrons and 11 protons. So there's 1 proton that's not being balanced out. Okay? So sodium now has a charge of positive 1. Chlorine has picked up an extra electron, so it now has a charge of negative 1. But they're both happy now because they got what they wanted. They got their outer shell filled. Now, try not to make us like a sociological comparison here, but they both got what they wanted. Their outer shells are full. Do they need each other anymore? Nope, they don't. Ionic bonds are very weak. Okay? They're very weak. They break easily. Okay? They break easily because, again, don't make a sociological reference here, but they don't need each other anymore. They got what they wanted. Okay? They got their outer shell full, so now they're good. Okay? So when you put ionic compounds in solution, that is, dissolve them in water, they split. Okay? And the charged particles float around separately instead. Which is why ionic compounds will conduct electricity when they're in solution, but molecular compounds will not. Okay? Because ionic compounds will break apart into their charged particles, and electrons can flow from one charged particle to the other, whereas when you put a molecular compound in water, it doesn't do that. So there are no charged particles, and electricity won't flow. Okay? So pure distilled water won't conduct electricity. Put a little bit of salt in it, and it'll conduct electricity out. Hey, Mr. Gay, what can I do for you?
Matisse, can I chat with you?
Yep. All right, so does that make sense about ionic bonds? Okay, so we got a metal, they're bonding with a non-metal, okay? We got now 2 charged particles, we've got electrons being traded, okay? It's a weak bond, okay, that doesn't last. Okay. Everybody okay with that? All right, so when we're naming an ionic compound, there's some simple rules to follow. Okay? The first thing is that we always name and write the metal first, okay? Because we go from left to right, okay? Metals are on the left, non-metals are on the right, so we go from left to right, okay? And we write, okay, the name of the metal first, and then the name of the non-metal second. So if I was naming this, for example, okay, what would the name of that be? What does Ca stand for? Calcium. And what's O? Oxygen. Okay, so the naming rules are, write the metal, write the non-metal, non-metal ends in ide. Okay, so instead of calcium oxygen is now calcium oxide. Okay, all we do is change the ending of the non-metal to ide. Okay, everybody all right with that? Okay, that's for simple binary ionic compounds. Okay, write the name of the metal, write the name of the non-metal, end it in ide, you're done. Okay, now, what if I have a compound that looks like this? What would that be? What's Mg stand for? Magnesium. Okay, and what does I stand for? Iodine. Okay, so we got to make it end in ide, so instead of iodine, it's going to be iodide. Okay, does the two matter? The two doesn't matter. In an ionic compound, we don't put in anything to represent the numbers, okay? And there's a reason for that, okay? Because a lot of people would look at this and go, magnesium diiodide, and they would put in a prefix on the iodide because there's two of them, except we don't use prefixes in an ionic compound because we don't need to. There's only one way that magnesium and iodine can go together because of their charges, okay? Magnesium gives up 2 electrons when it gets into a compound, okay? Its outer shell has 2 electrons that it needs to get rid of, okay? Iodine can only take on 1 electron. So when magnesium and iodine go together, there are going to be 2 iodines for every magnesium in order to make it work, okay? You guys remember the drop and swap? Okay? That's why we do the drop and swap, okay? This 2 comes down here, that 1 goes there, that's what balances the charges. The only way these 2 can go together is that way. So we don't have to say magnesium diiodide. We know if magnesium and iodide go together, they have to be 1 to 2. Okay? So there's never a prefix used in an ionic compound. All right, questions on that? Okay, so that should be the stuff that's familiar, okay, from Science 9. Okay, naming a binary ionic compound. Okay, so we got to remember, we got to name both ions in this, don't forget, okay, because sometimes people will just write like just the metal or just the non-metal and forget about something, I don't know why, okay, but okay, make sure you name them both, okay, and that we don't use any prefixes, okay, and here's another thing. The name of an ionic compound is not a proper name, okay, it's not like Jane Doe. Right, where you would capitalize the names. This is a designation, not a name. We say it's naming, but it's actually a designation. Therefore, it doesn't get capitalized unless you're starting a sentence with it. Like sodium chloride is great on fries. Then you would capitalize the sodium. Okay? But when you're naming a compound, okay, it is all lowercase because it is not a proper name. Okay, we also talk here about a true compound should have a net charge of 0, and again that goes back to the swap and drop method. Aluminum has a charge of +3, chlorine has a charge of -1, okay, so the 1 goes here, the 3 goes here, okay, 3 times -1 is 3, 1 times +3 is +3, that adds up to 0, the compound is good. Okay, that's why we do that drop and swap, to make sure that our compound has the same number of electrons and protons. All right. let's have you guys try just first 4 here. Okay, I want you to write the names of those compounds, and then we'll go through them together here in a minute or two. Okay, let's have a look at these 4. Obviously, we already did number 1, okay, earlier, okay, but we have an ionic compound because it's a metal and a nonmetal, okay? The metal is sodium, okay? The nonmetal is chlorine, so sodium chloride. Simple as that. Metal first, nonmetal second. All right, for number 2, we've got potassium and fluorine. So this stuff will be potassium fluoride. Okay, what number 3? Is hydrogen a metal or a non-metal? It's a metal. And it can behave as a non-metal as well. It's weird, okay? It's the simplest element. It can actually kind of go both ways, okay? But if it's listed first, like it is here, it's a metal, okay? If it was listed in a compound like this, it would be a non-metal, okay? So hydrogen's one you have to watch because it can behave both ways, okay? If it's listed first, then it's a metal. If it's listed anything other than first, it's behaving as a non-metal, okay? All right, so in this case, it's behaving as the metal, so we're going to write that this stuff would be hydrogen iodide. Okay, and then we have our last one here. We've got calcium as the metal and bromine as the non-metal, so this will be calcium bromide. Do we need anything to denote the 2? We do not. All right, does that seem familiar? Ringing a bell from last year? All right, let's have you guys do 2 more, and then we'll get our desks and stuff wiped down and get ready to go.